and we'll begin from the current slide. We'll begin from, there we go. Okay, we already did example 8. And PowerPoint is, okay, there it comes. It's very, very slow today. All right. Okay. Here's the other announcement. Sorry about this, folks. I think I told y'all at the first of the term, I have a mild form of leukemia, and I have to see my hematologist every few months. And the trouble is, he only sees patients on Tuesday mornings. So, next Tuesday is it. I've got a 10 o'clock appointment, but I have to be in for labs at 9 o'clock, which means if I came to campus, I'd have to leave by 8:15. And I don't think it's quite worth it to have 15 minutes of class. So, next Tuesday, we will not have class here. Now, we probably need to talk. I hate to miss a class, like crazy. I hate to miss a class, and we have possibly 2 options. Okay, we're not exactly in sync with where we were, I think it was last spring when I last taught this course, but that class is out there on YouTube videos. Now, you can either find the class and say, listen to this, do these assignments and stuff like this. It's all there. Or you don't get a chance to ask questions and interact then. We can try to make up the class. But if you think about my schedule, the only office hours I have available are Monday and Wednesday afternoon from 3:15 to 5:15, or Friday morning from 7:45 to 11:45. Are any of those times that any of you can come? Those who can't come can still watch it on YouTube videos. But would that be, I know it's probably not convenient for a morning class, can anyone come at any of those times? Monday, Wednesday afternoon at 3:15 to, it'll be 3:15 to 4:30, or 3:30 to 4:45. It's something like that. You know, we can weasel it in any way we want to in that time frame. Monday, Wednesday, either this week or next week. Would that be a good time to make up the class, or Friday morning? Anyone make any of those? No? Okay, you want to just, what we'll do then on Thursday, remind me to point out to you on YouTube video probably where that will be, and we'll count that for the class. You just watch the YouTube video and do the assignments I say on it. I do the same thing every time. Now, the only little issue may be, I don't think it'll be at all, but in case it does happen, if some of the numbers don't quite match, as in if I mention a page number or mention exercises into the section, they may be off a little bit, because last spring I was teaching from the old edition, and this fall I'm teaching from the new edition, so there may be some very minor, insignificant, can I get your name, please? Josh, okay. Minor, insignificant changes there, but I think you'll be able to pick up on those. Now, Josh, I was just saying, next Tuesday, 1 week from today, I have a doctor's appointment at 10 o'clock in the morning. I have to be there for labs at 9 o'clock, so if I came to campus, I'd have to leave there by 8:15 to get back to the labs, and that wouldn't be worth it. So we're not going to have class next Tuesday. But I will tell you, remind me on Thursday to, when we finish the class on Thursday, to look at the YouTube videos and say, this is the one you need to review for the Thursday's class. It won't match exactly, but it'll be pretty close. Okay? So next Tuesday, you get to snooze in a little longer. Okay. All right. And the sad news is, my 9:30 class is white slick too. I usually like, when they ask me, I say, early morning, the first possible appointment or the last possible appointment. I think it's 11:45 is the last time he sees a patient. And if I can do the first possible, then I don't miss as much class. I prefer the latest possible because I can get this class in and maybe even a little bit of the second class, but then I'll probably miss a little bit of the other. They put it smack dab in the middle of the morning. It wiped out this class and the next class and possibly some of my third class because I have another class that made, at 11 o'clock. So it couldn't have been at a worse time. But anyway, that's happening. One other thing, okay? Ms. Nyla Gerasi, a full-time math instructor on the Birmingham campus, is heading up the coaching of the math team. We do have a math team. I think the name of it, or the prime mathematician, I don't remember what they call it. Prime numbers was what my suggestion was. They modified that. But anyway, there is a competition coming up sometime, I think the first Friday in October. And so if anyone's interested, it's a fun time. It's not anything backbreaking or anything else. It's a good time, and there will be practices. And she said she could come out to this campus. I can meet with anyone who wants to meet and do practices. But again, I'm limited to Monday, Wednesday afternoon, 3:15 to 5:15. But we can have practice sessions then. So if anyone's at all interested in the math team, please let me know. Or contact Ms. Gerasi. Her email address is ngerasi, that's JARAYSI @lawsonstate.edu. Can I get your name, please? Huh? Ebony, got it. Good deal. All right. Sorry, I have to say it again. Ebony, I was telling the rest of the class, next Tuesday morning I have a doctor's appointment at 10 o'clock, which means I have to be in for labs at 9 o'clock, which means if I came to campus, I'd have to leave by 8:45 to be back at the Kirkland Clinic before, and parked and everything before 9 o'clock. So we will not be having class next Tuesday. And I tried to find the time when we could make up the class. Nothing worked. So Thursday I will go over right at the end of the class, show you the YouTube video that will best fit with what we would have covered next Tuesday. That will be your assignment for what you should do on Tuesday. The weekend, whenever you want to do it, just get that done, and we'll pick up from where it leaves off on the following Thursday. We will have class today and Thursday, not next Tuesday, but we'll be back then. Okay. Any questions? And if you're interested in the math team, please see me and let me know. Okay? Any questions? All right. I think I started off showing this last time, didn't I? Example 10. Didn't I hold the book up here and show you the slope of this number of alternative fuel stations increased dramatically, pretty steadily for the first 4 years, and then the next 4 years leveled off a little bit, still increased, and that's why you had a piecewise defined function. Didn't we talk about that? Okay. So let's actually do it, okay? We're not going to do all of it because it's take way too long, but we'll do some, okay? Here is that piecewise defined function. If I can get the pen to work. Still not. There we go. I think, yeah. Okay. Here's the piecewise. It's number of stations as a function of time measured in years. And this will be 260.8 T minus 439. And this is good for T between 8 and 11. Now, remember what that means. Those are years, 2008 until 2011. It just dropped off the 2000 part and used the last two digits, 8 to 11. Okay? Now, this was done by a linear regression model that came up with that thing. It's not exact, it's approximate. Then for the next 4 years, it followed this pattern. 151.2T plus 714. And this was good for 12 to 15. 2012 to 2015. So pretty current data. This is probably actual data. I don't believe they made this up. The source here is Alternative Fuels Data Center. Okay? The number of stations offering alternative fuels increased dramatically from that first 3 years, 4 years actually, and then leveled off but still had an increase. Why do I say increased dramatically? Look at the slope here. What would that be measured in? This thing here, 260.8T. Number of stations per year. That's what that stands for. Now, your y-intercept, that just shows if you projected that backward to year 2000, you wouldn't have had it have been negative 439 stations. That doesn't matter because 2000 is not in your domain. So pay very little attention to that. That just gives you a starting point to get your curve right, your line right. Then for the next 4 years, 2012 through 15, still had a significant increase, but just not as big as it was the previous 4 years. 151.2 stations per year. Now you don't start 2.2 stations there. So this is just a number that came out of the linear regression model. But about 150 stations per year here, about 260 stations per year the first 4 years. That's what the model is showing you. Okay? Now, with that in mind, use that function to approximate. This won't give you anything exact. Approximate the number of stations that sold E85 gas each year from 2008 to 2015. Okay? Let's just do 2008, okay? How would you determine how many, or estimate how many stations, what would that be represented by? S, okay? S of, and what did you say? Of 8, okay? And pull out your handy-dandy calculators. That'll make it a lot easier, but you can do it without that. If you plugged in an 8 there, that would be 64. Carry a 6, that would be 6, okay? That would be 48, carry a 4, 2,000, minus 439. Now I'm doing this in my head, I may be making a mistake. I think that comes out approximately 647, approximately 647 stations. Now doing it in my head, how close am I? Or 16, I'm sorry, left off the 1. 1,647 stations. See how it works? Plug in the year, estimate that. Now, why did I leave off the 0.4? Yeah, who cares about 0.4 of a service station? I mean, no, we're estimating anyway. I would say for an estimate, make that 1,600, 1,650. That would be as good a number as any. Okay? Now what you can do is compare that then with the actual data here. And in 2008, I can't tell any closer than that. It's better than 1,600 looking at the graph in the book, but I can't get it any more precise than this. This actually gives me an idea, probably better than looking at the graph. So that's on the actual data. Okay? Want to jump on to 2011? How would you do that one? S of 11, and what would we do with that? This one I will not do in my head, okay? That would be what? 260, because we're still in the domain of the first equation, 260.8 times 11 minus 439. Hopefully some of you have a calculator. What does that give you? 2,000 what? 429 approximately. Good deal. Can I get your name, please? Second? Sandria. Okay. Got it. Good deal. All right. Y'all will hear this a few times, I guess. Next Tuesday, I have a doctor's appointment at 10 o'clock. I have to be there for labs at 9 o'clock. That means if I came to campus, I'd have to leave by 8:15. It would make a lot of sense to have a class for 15 minutes. So what we're going to do, I tried to find the time that would work in my off hours and yours, and nothing worked. So what we'll do on Thursday, I'll find the YouTube video that most closely represents what we would be covering on next Tuesday, wherever we leave off on Thursday. And then that will be your assignment. Listen to the YouTube video, do whatever the assignment is from that video. Okay? So that will be next Tuesday. Sorry about that. All right. We're doing example 10 at the top of page 42. Let's do the next part. It says each year, I'm just doing selective years. Let's do year 2012. What would be S of 12? Where do we go here, Waldo? Yes, we use the second one because 12 is in the second domain, not in the first domain. So this will be 151.2 times 12 plus 714. Someone punch that in and see what you get. A little louder. And what does that give you? Total. Okay. Oh boy, he's quick. Okay, 2,528. Very good. So you see it's still going up, but not at the same rate it was before. Let's jump over the 15. S of 15, I'm just doing selected ones. That would be what? How would you get it? 151.2 times 15 plus 714. And what does that give you? 2,900? 18 or 80? 82. Okay, I can't hear well. All right. Unfortunately, it's not an audiologist I'm seeing on Tuesday. It's my hematologist. Sorry. Okay, do you see how that works? Okay? With a piecewise defined function, whatever your input is, you have to find which piece that goes with. Plug that number into that equation, and then do your calculations from there. Any questions? All right, there is a checkpoint. Remember, every one of these examples pretty much has a checkpoint, and if you can't, I would suggest, do the checkpoints as soon as you get out of class. The first free period you have, try to do the checkpoints, and if you can't get a reasonable answer, then look at the audiovisual solution at larsonprecalculus.com. All right, any questions? All right, now we're moving to difference quotients. Anyone ever heard of these before? Okay, some of you have. Let me tell you, all of you have. You just didn't call them that back then when you were doing it, okay? What does difference mean? Subtraction. What does quotient mean? Division, okay? Guess what? You've all done these. Whether they called them difference quotients or not, you have. One of the basic definitions in calculus employs this ratio, okay? Now, you're not in calculus yet. Hopefully, most of you will get there, but don't fret it if this looks foreign to you. But this is what you're doing. It's f of x plus h, where h is some small number slightly larger than x, okay, minus f of x. So, y'all remind me, what does f stand for, f of x? Say again? Y, okay. F of x is y. Remember that, the key thing. So this will be your y value at a number slightly more than x minus the y value at x. That's sort of like a y2 minus y1. Oh, wait a minute. And then your x's are x plus h minus x, right? X plus H minus X. The X's cancel out. What are you left with? H. So this is nothing more than a, what's y2 minus y1 over x2 minus x1? Slope. I told you all have done these before. You just didn't call them a difference question. That's exactly what this is. This is a slope of some nature. Now, of course, H can't be equal to 0. This is where calculus comes in. H can't be equal to 0, but in calculus, we let H approach 0. Get closer and closer to 0. Because if this were a slope, you'd have 2 points. And that would be the slope between those 2 points. What you do in calculus is let those 2 points get closer and closer to each other. In other words, H gets less and less and less, and then you do the strange thing they call a limit. Is there a limit as H is approaching 0 of what that ratio is? And that's where we get our difference questions. Okay? Don't worry about that till you get to calculus, but that's what you're doing. And they have a special name for that in calculus. Does anyone happen to know it? Second? The name for that thing, that limit, is different quotient as H approaches 0. What? Not quite, okay? A lot of times when you are approaching something that is 0, you do reach an asymptote. This is called a derivative. That's what a derivative is in first quarter calculus, is the limit of this as H is approaching 0. If it exists, okay? But you don't have to worry about that. All we're worried now is the difference question. And I think example 11, that's what's coming up next. So how do we evaluate this difference question? What would you say? Say again? Plug it in. I love it, okay? What do we plug in first? Okay, let's plug in x plus h, right? That's what you plug in. And what does that give you? Oh, we've done it. I know it was a week ago, but we did it. X plus h squared minus 4 times x plus h plus 7. Okay, let's evaluate it. See what it is. Anyone know what x plus h squared is? Oh, very good. X squared plus, what do you say? 2hx plus h squared. You may have said x, h in the middle. It doesn't matter. Okay? Minus. Oh, does anybody know how he got that? Okay? When you're squaring a binomial, square the first term, twice the product of the 2 terms, square the last term. If you don't remember that, write it down. X plus h times x plus h and FOIL it. You'll get the same answer. Okay? Either way you do it. Next. Minus 4x. Minus 4h. I used to be in that. Okay? Plus 7. All right. There's your f of x plus h. And that's the first thing we do in our difference quotient. What's the next thing we do in our difference quotient? Subtract. Okay. Now put that in parentheses. Your f of x is that. X squared minus 4x plus 7. Okay? And we take that and divide it by h. Right? Everybody see that? Okay? It's a little long, but nothing fancy. Okay? So let's clear those parentheses over there. You got a lot of writing to do. X squared plus 2hx plus h squared minus 4x minus 4h plus 7. Now, what do we get here? Minus x squared plus plus, say again, 4x minus 7, all divided by h. Now what do you do now? Combine like terms. Do you see any like terms here? I'm sorry? Because I needed to have them written out before I combine them. But, I mean, what do you mean?
Like, before we put it all over H, why don't we just go ahead and combine terms and then
Oh, you mean do all the numerator first and then at the end? You could do that, as long as you remember to. See, I'm old and I tend to forget things real easily, so I write them all out. But, you know, as long as you remember, certainly you can do that. Okay, I understand what you mean now. But what do we do now? And what like terms do you see? X squared and minus x squared, those add to 0. Say again? A little louder. H squared, there's only one h squared in there. Oh, here's a minus 4x and a plus 4x, those add to 0. Oh boy, okay. And you have a plus 7 and a minus 7. Those add to 0. What do you have left? 2hx plus h squared minus 4h, all divided by h. What can you do now? Oh, you can factor out an h in the numerator. What would that give you? H times 2x plus h minus 4. And divide that by h, and now what can you do? Oh, the h's divide away. And there's your difference quotient. The difference quotient is 2x plus h minus 4. Okay? You want me to jump ahead to calculus just for a moment here? You don't need to know this part. But you see what we do here? We take the limit of this thing, because that's the limit of that thing. As h is approaching 0, the closer h gets to 0, what does this approach? 2x minus 4. And guess what the derivative of that first expression is? 2x minus 4. Okay? And later, if you take calculus, you'll say there's an easy way to do it. Yeah.
So looking at the first hand, so you're looking at, instead you get 2x minus 4.
Right.
Exponent times.
You got it. You've had a little calculus, huh? Okay. You take the exponent times the coefficient and drop that by 1. That would give you 2x. And then exponent here, 1 times the coefficient minus 4. Drop the coefficient by 1. That makes x is 0, which is 1 minus 4. You got it. You have just taken your first derivative, whether you realize it or not. Didn't even know what a derivative was, huh? Well, you've just done it. Difference quotient is used for that. Okay. I'm sorry that got written in the background. Okay. Any questions on that? Your difference quotient, you leave the h in it. Okay? We aren't taking limits yet. That's your difference quotient right there. Was there a question? I thought I heard something. Any questions? All right, let's clear this out of the way so we can let them show how they did it. It won't be as neat as we were, but we can do it. Okay, here's your solution. They rewrote what we're looking for, and then they wrote what the alpha of x plus h was here. We did that. Minus alpha of x, they did that. And they put the h underneath. Sorry about that. They're sort of old and decrepit too. And then they multiplied out the top term, which is x squared minus 2xh plus x squared minus 4x minus 4h plus 7 minus x squared plus 4x minus 7 over h. And then when you combine like terms, like we did, the x squares go away, the 4x's go away, and the 7's go away, and you're left with just 2xh minus plus h squared minus 4h divided by h. Then divide out an h from the first term, and you have left 2x plus h minus 4 over h, and then the h's divide away, and you're left with 2x plus h minus 4, as long as h is not equal to 0. That was part of the original problem. It still is, but who cares now? It's no longer in the denominator. Okay? But as you let h get closer and closer to 0, this goes closer and closer to that, meaning the slope of that, what we call a secant line, is getting closer and closer to what we call the slope of the tangent line when the h goes to 0. And that's what a derivative is. Not that you need to know that, but that's where we use these different questions. But these are nothing more than a slope formula, just written in function notation rather than y2 minus y1s, you know, that kind of stuff. Okay, they skipped. No, they didn't. This is a summary of your function terminology. Okay? Looking back over the whole section here, function is a relationship between two variables, okay, such that to each of the independent variable, the first one, there corresponds only one value for the dependent of the second variable. Your function notation, best thing to remember in the course, y is equal to f of x. If you got that down, you got most of the functions covered, okay? F is the name of the function, who cares? Fred, you can name it anything you wanted to. Y is the dependent variable because it depends on what value you put in for x. X then is independent variable. You put anything you want to in there as long as it's in the domain. And f of x is the value of the function at x, which is also the value for y, because y is equal to f of x. The domain of the function is a set of all the values or the inputs that you can put in for the independent variable. In this case, it would be x. It doesn't have to be x, it could be anything. If x is in the domain of f, then f is said to be defined at x. If x is not in the domain of f, then x is said to be undefined at x. Don't even put it there. That's why back on that alternative fuel problem, to put a 0 in there and say, oh, you had negative notation. No, you didn't, because 0 is not in your domain. So it makes no sense to put that in. Okay? The range of a function is the set of all the output values assumed by the dependent variable, that is the function values, the y values. And then the implied domain, if f is defined by an algebraic expression and the domain is not specified, you don't say between years 4 and 11 or something like that. If it's not specified, then the implied domain consists of all real numbers. You always start with all real numbers as long as that expression is defined. What two major things do we look for that give you undefined issues in your domain? Yes, you can. If you have a variable in the denominator, that denominator can never equal 0. You're absolutely right. And the second? Yeah, if the variable is inside a radical, especially a square root, or even any even root, what is true about that entity that's inside there? It cannot be negative. It has to be greater than or equal to 0. You got it. All right, good deal. That was the end of the section. We do have some vocabulary. First, page 44, 4 questions here. Fill in the blank. A relation that assigns to each element x from a set of inputs or blank set of inputs. Say again? No, inputs or what you call that set? Domain. Exactly one element y in a set of outputs. What's the set of outputs called? Range. That's called a blank function. You got it. All right, good deal. Number 2. For an equation that represents y as a function of x, the set of all the values taken on by the blank variable x. What the variable x be called if y is a function of x? The which? Say again? Independent variable. Excellent. I can't hear well, so you have to spec out. Okay. Independent variable x in the domain, and the set of all values taken on by the blank variable y Dependent variable y is the range. Very good. Number 3, if the domain of a function is not given, then the set of the values of the independent variable for which the expression is defined is called the, y'all are looking at the board, aren't you? Implied domain, you got it. And number 4, one of the basic definitions in calculus uses the ratio f of x plus h minus f of x divided by h, where h is not equal to 0. That ratio is called the blank blank. Difference quotient. Very good. All right, that wasn't on the slide, but y'all remember it. Good deal. Homework exercises then. Do either 5 or 7, or both. And by the way, 7 is given in, remember this book has a new feature that the previous book didn't. Calc Chat has all the worked out homework exercises in it. Odd numbers.
Can you spell that like cow chat?
Yeah, you don't have a book yet.
Oh, I do have a book.
Okay, it's on the front cover.
Gotcha.
Okay? CalcChat.com. The ones that are bold or red, the red letter ones, those are worked out in CalcView.com. And someone in this class told me that that's on, you can get an app to do those. So you can do it on your phone even. So that's why go and do, homework anywhere that you have a phone, you can check them, right? So you don't have to be limited to your desk. Say, I can't do it, I was on the bus. Now you can do it on the bus. You can do it in the library. You can do it anywhere you want to. Okay. Talk about homework. Okay. Now, do number 9. It has 4 parts, so do number 9. Do any of the odds 11 through 17. 11 is on CalcView.
Oh, I have a question.
Yes.
Okay, you said 17 was a function. How is 17 a function? Look at number 17.
Okay, say this again.
How is number 17 a function?
Oh, how is 17 a function? Y is equal to minus 75. How in the world is that a function? Say again? Okay, let's first see what it is. Determine whether the expression y represents a function of x. Okay? No, x is not negative 75. That's what y is. So is that a function? She said it was. Okay, did they get it wrong? Okay, give me an x. 4. What's y? Negative 75. Give me another x. Oh, yeah, for any x you give me, there's only one y. Negative 75. That has a special name. Constant function, exactly. It's always negative 75, so it is a function. For any x value, there's only one y, because there's only one y for any of them. Okay, so that is definitely a function. Good deal. Good question. Then any of the odds, 19 through 29. Any of those are on CalcChat.com if you're having trouble doing them, but number 21 is on CalcView.com. Okay, any of the, either 31 or 33, or both if you choose, and neither of those are on CalcView. Any of the odds 35 to 41, 37 is on CalcView. Either 43 or 45, or both, 43 is on CalcView. Either 47 or any of the odds 47 through 55, and 49 is on CalcView. And then any of the odds 57 through through 71. Okay, any of the odds, what was it, 57 through 71? Yeah, 57 to 71. I would do a few of those. Now, I didn't see any of them on CalcView. That's a shame. They should have. And then do any of the odds 75 through 79. These are the ones we just started today. 75 is on CalcView. Either 81 or 83, or both. Neither of those are in CalcView. Okay, now they also have, most of these exercises are, what do they call them? I think they call them exercises, don't they? Yeah, exercises. They have what they call exploration. Okay? These are pretty good to do. There's usually one or two that are true, false. Good to think through. Don't expect to see any true, false on the test. That's really a guessing game there, so I don't expect to see. I'm not going to say you'll never see one, but you don't expect to see them. But anyway, those, think through why is it true, why is it false, is definitely worth looking at. And then there are a few like 89. I really don't like 89 because it actually is saying something's true when it's not, and they put the big red X. But anyway, think through 89, 91, 93. Any of those, you don't really have to work anything out, but not a bad thing to think through. Any questions? Yes.
Are we gonna have vocabulary questions like the stuff on our trees?
I doubt it. Okay, that's so you'll know what we're talking about. So when you're reading a question on the test, you won't say, "What in the world does that mean?" But no, it's something we'll do in class just to get you prepared for that. Any other questions? 1.4. Say again? I couldn't hear you. Oh, after the end of 1.6. Okay, when we finish 1.6, I'll give you the quiz. Good question. All right. Any other questions? All right. Then we'll move on to 1.5. Hopefully this will go a little more quickly than 1.4 did. It's still a long section, but not quite as long as the one before, if it'll ever come up here. I'm sorry, PowerPoint takes so long to load. All right, here we go. All right, still doing chapter 1, functions in the graphs. We haven't really gotten too much on graphing yet, but we'll get there. That's what 1.5 is, analyzing the graphs of functions. Okay? What we'll do, I've already introduced this concept to you, the vertical line test, as a test for functions. We'll find zeros of functions, and we actually have already done that too, kind of, in one of the exercises. We'll determine intervals on which functions are either increasing or decreasing. I don't think we've done that one yet. And we'll determine the relative maximum and relative minimum values of functions. We'll determine the average rate of change of a function. That sounds like something new, isn't it? No, it isn't. Something we've just done, but we'll give it a different name. And we'll identify even in odd functions, which we haven't done yet either. So let's first look at the graph of a function. We've studied functions from an algebraic point of view, okay? That's what we're mostly looking at in 1.4. In this section, we will study functions from a graphical perspective. The graph of a function is a collection of the ordered pairs x and f of x. What's f of x? Y, good, okay? Such that x is in the domain of f, okay? So these are your x-y pairs, just like you graph two variable equation. Pick an x, calculate the y, or vice versa, okay? So that's what we'll be doing. We just didn't call them domains before, okay? As you study this section, remember that x is the directed distance, okay, when you write your function y is equal to f of x. And this is why I don't like to call it even. Everybody calls this what? What's that? We always call it the x-axis. The better name for it is the horizontal axis. It doesn't always have to be x. It could be t. It could be anything else. Okay, and what do we usually call this? Yeah, but really it's the vertical axis. Okay, but when it is y is equal to f of x, then that is the x and y axis. Remember, then your x value is the distance from the y-axis, right? If this is your y-axis, how far are you over here? You're 1 unit away here, 2 units away there, minus 1 unit away here, meaning 1 to the left. And the y is the directed distance from the x-axis. Here is at 1, here is at 2. Okay, that's your distance from the y. Okay, you know this, I think. Okay, so is that a function, by the way? Can you tell me definitely whether that's a function or not? Yes, it is. Okay, we won't go into why, but that is a function. Because for any value x, you have a y, and only one y. That does represent a function. Okay? Any questions on that? Was that nope? Okay, good. Okay. I thought there was a question. Use the graph of the function f in this figure to find what is the domain of f. This is the graph of f. What's its domain? From -1 to 5, but it's not 5, but it does include -1. Everybody see that? -1 is in that domain, 5 is not. How do you know it's not? Open circle, meaning up to 5, yes, 4.9999999 is in there, 5 is not. Okay? -1 is in there. So your domain is, and how would we express that in whichever notation you choose? Second? Let's do interval notation. How would you express that in interval notation? Bracket, -1, comma, 5, parentheses. Got it. That's how we do it. If we did it otherwise, you would say the set of all x's, because the x's, when you draw the x's, if you label, that's the x, y. In this case, it is the x and y axis, okay? Because y is equal to f of x. Yeah, they didn't say that anywhere, they showed it to you here. Okay? The set of all x's such that x is less than or equal to -1 and -1 is less than or equal to x. Let me write that down since I'm saying it so poorly. The other way to do this, the domain of f, this is what my notation, the book doesn't use this, would be the set of all x values such that -1 is less than or equal to x at less than 5. That's how you write it in set notation. Okay? Set of all x's such that -1 is less than or equal to x and x is less than 5. Okay? Or in interval notation, sure, interval notation is a bit more concise here. Okay, second question. What's the function value f of -1? How would you get that? Plug it in, plug it in. Plug in -1 here for x. That's what goes in here, f of x. That's your -1. Then find out what the y is. There it is, 1. So that would be 1. Okay, how about f of 2? Go across here to x equal 2. Find the function. There it is. And what's the y value? -3. So that is -3. Everybody see this? What we were doing algebraically, we're now doing it from the graph. Now the question, what's the range of f? Say -3 to, how do I put that in? Bracket, -3, comma, 3, close bracket, because it includes both of the endpoints. Exactly. How do I write that in set notation? The range of f, braces, set of all y's such that -3 is less than or equal to y less than or equal to 3. I can't write a 3. Okay, that's pretty ugly. Let's see if I can make that a little bit better. All right. Everybody see that? All right, there's your range. All right. that was example 1. Any questions? Let me clear, well, I think I can just go on and do this. Okay, the closed dot at -1, 1. What does -1, 1 mean? Is that an interval? No, that's a point. That's the only problem with interval notation. You have to be able to distinguish what's a point and what's an interval. That's a point, okay? What does this stand for? X value, Y value, exactly, okay. The closed dot at -1, 1 indicates that at X equals -1 in the domain, therefore, and that's where the domain begins. The open dot at 5, 2, again, that's a point. Those are coordinates of the point. X equals 5, Y is equal 2, indicates that X equals 5 is not in the domain, but -1 is. So therefore, we write, so the domain is, and they wrote it in interval notation, all the values of X from -1 to 5, but not including 5, including -1, but not including 5. Very good. Now, how do you know that all those values were in there? Because the line is connected. The curve is solid there. There aren't any things. Remember earlier we had one that you had a point here, a point there, a point there, a point. If there are points there but nothing in between, then the domain is that value, this value, yeah. But if you got everything colored in between, you have an infinite number of ordered pairs. Yes.
So if it was like separated at one point, would you use a union in the
Second.
if it was separated at one point, would you use a union?
You could do union. Oh, okay, I got what you mean. If there was one separation here, okay, say it went from here, but then didn't have anything here and it started here again. You would say it's the set of all values x's such that x is -1 to 0, inclusive. Union that with, that's what she's saying, from 2 to 3, 2 to 5, where 2 is included with 5 is not. Yeah, that's where you use the union definition. We'll get there later, okay? So there's your domain, and then just like we did, we found that f of -1 is equal to 1, f of 2 is equal to -3. You just use your graph to find those. And then finally, because the graph does not extend below f of 2, which is -3, or above f of 0, which is 3, the range is the interval that includes both of those values, -3 to 3. Very good. All right. The use of the dots, whether they're open or closed at the extreme left and right points on a graph, indicate that the graph does not extend past those points. This graph even, it doesn't extend over here because you don't see anything there. It has a dot there. It doesn't extend there because you have that dot there. Now these dots are here too. Those are just to show the max and min. We're going to get there later. You don't have to have them dotted, but you did. Now, if this function, remember that very first one we had? Let's go back to it. Oh, that one. Okay. This one has no dot at the end, so this one extends, as far as we know, from negative infinity to positive infinity. Because nothing indicates it stops here or stops there. It's just where the drawing stops. If it had a dot there and there, that means it terminates there. Okay? Oh, okay. Nope. Yeah. Okay. So this one, if such dots are not on the graph, then assume that the graph extends beyond those points. And if there's no other, nothing showing anything else, you assume they go to either negative or positive infinity. Okay? If that were the case, you may know the domain of the function, negative infinity to positive infinity, but you have no clue of what the range is because you don't know how far. But if that's going down like this and there's no indication it stops, then that'll be negative infinity to positive infinity. However, if it does something like this, it doesn't ever seem like it's going back up, then the range may be different. So you can't tell everything, but you can tell a lot. Most of the time it'll be pretty obvious. Okay, by the definition of a function, tell me what has to be true. For any given input, one and only one output. So any x value, you can only have one y value. That gives you a way to identify a function of a graph, whether it's a function or not. That means that the graph of a function cannot have two or more different points on the same x coordinate. So if you have an x coordinate here, you can't have a y here and here, or y here and here, or even there. You can't. Okay? It means that the graph cannot have two or more different points on the same x coordinate. Well, what is x coordinate? That would be a vertical line. On that vertical line, you can't have but one intersection. You may not have any, but you can't have more than one. Okay? And those 2 points on the graph of the function can be vertically above or below each other. It follows then that the vertical line can intersect the graph at most once. It may not intersect at all, but it can at most intersect once. That gives you, that observation provides a convenient visual test, vertical line test. If you have a graph of a function, if there's no vertical line that crosses that graph more than once, it is a function. If there is at least one vertical line that has more than one y value, not a function. So the vertical line test for a function, a set of points on a coordinate plane is the graph y as a function of x, if and only if no vertical line intersects the graph more than once. Okay? Now, blah, blah, blah. Okay? They don't show this on the slide set, so let me do it here. Notice at home you won't be able to see this, okay? This first, example 2, is that a function? A. No, because that vertical line crosses twice. Now this vertical line right here only crosses once. That's the y-axis. Over here you don't have any, that's no problem. But if you have at least one vertical line, and here you have infinite number of vertical lines that will cross twice. How about this one? Yeah, that would be a function because there's no vertical line you can draw that will cross more than once. How about this one? Say again? I couldn't hear.
Yes.
Yes, it is a function because even though some vertical lines won't cross anywhere, all the other vertical lines will intersect at most once. So those B and C are functions, A is not. Okay. And there's a checkpoint there as well. Okay, now we go to the zeros of a function. Okay? If the graph of a function of x has an x-intercept, in other words, it's some value a on the x-axis, the y value there is 0, then a is said to be a 0 of the function. In other words, the function is equal to 0. In other words, what is the f? The y. The y is equal to 0. That means that's a 0 for the function. Zeros of the function, f of x, are the x values for which the y, f of x, is equal to 0. And you may have more than one. Right? You can't have, for any given x, more than one y value, but you could have several different x's that all have y values of 0, or anything else. So those are the zeros of the function. We actually did some exercises in the first section like that. Yeah. What's that? Okay. Yeah. Linear functions can only intersect at most once. Okay, unless y is equal to 0, it intersects everywhere. Okay, but yeah, any other function may intersect more than once. A quadratic function, square, most that can ever intersect is twice. Cubic function, most that can 3, but it doesn't have to do 2 or 3. Yes?
Okay, so when you find the zeros in the calculator, you can just plug it in and then see the graph and then it'll be a 0. But I know you're going to probably show some mathematical way. So if you do it on the test and we just have a calculator and we just put in what the zeros are you going to take off for not showing the work?
Okay. Let me phrase that a different way. If you show your work, I can give partial credit. If you get it right, you get it right. Okay? however you get it. Okay? If you do the work but don't show it, I can't tell. All I can do is mark it wrong. If you show your work, I can get partial credit if you're heading in the right direction. If you make a dumb mathematical error, I can give you partial credit. So I like for you to show works because I like to give as many points as I can. But if you rob me of that opportunity, I'm sad, but I have to. Okay? Does that answer your question? Yeah, if you do it and you get it right, you get it. Okay. All right. Sad again. We're out of time. But I think we have time for a few homework exercises. We'll start next time with example 3. Let me mark that in my book before I go any further. Okay? And homework exercises here, you can do either 7 or 9. 9 is on Calc View. You can do 11 or 13. 11 is on Calc View. And stop there because we didn't do any finding. We just talked about finding zeros of function. We'll pick up from there and go from there. 7 or 9 or both. 11 or 13 or both. All right, good deal. All right, and we'll hopefully finish 1.5 next time and move on to 1.6. Because I know y'all are anxious to get your quiz. Good deal. We will have class Thursday. We will not have class the following Tuesday, but I'll tell you Thursday where to go on YouTube to pick up the class. And by the way, no one who came in late left the umbrella here last time because someone found it. Good deal. Okay, Kaylin didn't come in. As far as I know, Walter didn't come in. Serenity didn't come in. And Todd didn't come in.